Good evening, everyone. Myself, Gautam Sarma. I welcome you all in a Sapience Education. So today I am going to discuss some part. This is part 3 video of the electrostatic potential and the capacitance. So I will go one by one. Okay. So first topic in this part 2, part 3 video is that electrostatic potential energy of a system of a charges, right? So what do you mean by electrostatic potential energy of the system of a charges? So let us assume that there is a charge. Let us assume that there is a single charge system, okay, and from infinity to this point, if I have put this charge, so is there any work is done against anyone? No work is done. So here work done is zero. Work done in bringing a charge q1 from infinity to this point will be equal to 0. But now at the same time, if there is another charge q2 which is at an infinity, and I want to bring this q2 charge at this point which is nearby this charge, so what will be the work done? So as you know that when you move this to this direction, so we have to work against the work against the electric field right? See here, this charge will create an electric field like this, and due to this what happen, if you bring this charge, so what will happen, you have to do the work. So as soon as I have to do the work and put this charge, so this work gets converted into potential energy, right? It is as simple as it is. See here, I have already done in a previous classes also, I have already discussed these things, that if there is a body like this, and if you lift this body, so what will happen, you are going to do work. For example, you have done the work of 100 joule, put this body to this area. So when you put this body to this area, so what will happen, uh, there will be an increase in the potential energy, and this potential energy will be equal to 100 joule only. So whatever work is done, so that gets converted into potential energy. Here also the same example is there. If there is no charge around it, and if I bring this charge from infinity to this point, so no work is done. But when another charge q2, which is brought from infinity to this point, so this is the region of electric field created by this q1. So we have to do the work. So the work done will be w2. So work done is equal to work done, total work done. If I will calculate total work done, that is what W net. So this will be equal to W1 plus W2. So when we add on, and this work done will be equal to the potential energy, because whatever our work is done, that is being converted into potential energy. So we can directly say that the potential energy of the system will be equal to net work done in bringing a charge from infinity to this point. Total work done in bringing a charge from infinity to this point. I hope you have understood now. Now let us check it, what it says. Work done in assembling a system, that is equal to potential energy of the system. U indicates for, you should understand that U indicates potential energy, right? Potential energy. Okay. Now for a system of a two charge. So first I will discuss about the for a system of a two charge. So step by step. Work done in bringing W1 will be equal to 0. Why 0? See, I have already discussed this point here only, that if you bring a charge Q1 from infinity to any point, but there is no extra electric field, so what will happen? No work will be done. Against whom you will work? No, nothing is there. So that's why work done for the single charge is 0. By definition, work done potential is equal to work done per unit charge. Now, if you bring another charge Q2, which is at a distance of R12 from this charge, so what will happen? What will happen? So, work done in bringing a charge from this will be equal to what? Work done is equal to Q into B. Q into B. So, the charge is Q2, but what about the potential? So, the potential at this point. So, you know how to find the potential, right? Potential we have already discussed in the previous part of the video, that potential is equal to K Q1 or Q charge by R, right? KQ by R. Okay. So try to understand here. At this point, the potential due to this, we want potential due to this charge. So potential at this point V is equal to K into Q1. There will be Q1, right? Into R1 to 2. So we have got potential. Now, if this point has some potential and if we are bringing a charge Q2 from infinity to this point, so the work done, that is W2, will be equal to, work done W2 will be equal to potential into charge Q2. So finally we are getting here potential is equal to K Q1 by R12 into Q2. So finally work done W2 will be equal to K Q1 Q2 by R12, right? So we have got W. Now total potential energy due to system is equal to total work done. So the work done for a charge Q1 is equal to 0. Work done for charge 2 is equal to Q into K into R12. K Q1 Q2 by R12. So the total charge will be what? See, add on this 0 plus K Q1 Q2 by R12. So when you add this, so what will happen? Total potential energy of the system you will get. So finally potential energy of the system will be 0 plus this is equal to K Q1 Q2 by R12. So this is the potential energy of the system of a two charge, right? So I hope you have understood this, right? I hope you have understood that the potential energy of the system of a two charge, right? Now, if I will tell you that, is it necessary that if the charge is 3, so what will happen? So go step by step. So first of all, see here how smartly we can manage this to do. First of all, how many work done we have to mention? W1. Let us mention W2, and let us mention W3. And the total energy of the system, potential energy of the system will be equal to W1 plus W2 plus W3. Now the thing is that W1 will be 0 because when you put a charge at any position where no other charges is involved, so that can be W1. Now the thing is that W2, when you put, after that when you bring this charge Q2, so work done W2 is equal to K Q1 Q2 by R12. Just now we have derived this 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 work is done, right? Now the thing is that, what about work done? Third work done, this is W3. So let us consider here, I will erase this. Let us consider here that at this point the potential V is the potential. Now the work done W3 is equal to Q3 into B. Now the thing is that how you will find potential? See, potential at this point, that is V is equal to potential due to this charge and potential due to this charge. So that is equal to potential due to charge 1 V1 plus V2. So potential can be written as how? K Q1 by R13 plus potential due to charge 2 will be equal to K to Q2 by R23. If you don't understand this potential, so go through the previous video. I can't help it, right? So you have to go through that video, that how to find the potential. So here, see, similarly the work done W3 is equal to Q3 into P. So finally we are getting W3 is equal to Q3 into P is K Q1 by R13 plus K Q2 by R23. Now the thing is that U system, we want that system of three charges has how much potential energy. So this will be equal to W net. So W net is equal to W1 plus W2 plus W3. Now the thing is that, what are the values of the W1? So the 0. What is the value of W2? KQ1 Q2 by R12. And what is the value of W3? KQ1 into Q3 by R13 KQ K Q2 by R23. So let us add on. So if we add on, see here. So if you add on 0 plus 0 plus k q1 q2 by r12. So this is intensity k q1 q3 by r1, k q2 q3 by r23, right? So see here, one thing you have seen that first of all, if you have a two charge or three charges, one, two, three. So charge one, let us consider mm, if there is a three system of a charge and you have a charge q1, you have a charge q2, and you have a charge q3. Now you have to add k q1 q2 by r12. So due to this r12 we have added. Now q1 q3, so we have to add like this. q1 q3 is equal to k q1 q3 by r13. Now due to this one, so mutually we have to add like this. So you will get the system of a charge. So this is the potential energy due to three system of a charge. Now let us go for a summation. So if you go for a shortcut, so finally shortcut will be equal to k into summation of I is not equal to j. It should not be the condition. qi qj by r1j. If you put this, if you use this formula, so you can get this. See, for example, 5 charges are there, so you can 1 2 1 2 1 3 1 3 1 4 1 4 1 5 1 5 again 2 1 2 3, like this you can calculate it. In calculating potential energy, the values of all the charges are taken with their given signs. Yeah, very important. This is very important that you should always present give with the either it is positive or negative. So you have to put with a sign. Hence, potential energy of a system may be positive or negative. So we unable to tell this, right? Now, potential energy due to potential energy of a system of charges in an external field. Very good, very important. Now see here. As you know that without external field you have done easily. Now if there is an external field E, there is an external field E, then and now let us consider that the potential at this point potential at this point is B, and now you are bringing a charge from this point to this charge. So what will happen? So you can easily find work done, that is by Q is equal to B. So work done is equal to QB. This is very simple, right? So hence potential energy is equal to QB. Potential energy is equal to QB. But what about for a single charge only? We are not talking about multiple charge. Now the thing is that if you bring a charge, let us consider Q1 here, and another charge you want to bring. So what will happen? Let us suppose here potential is V1 and the another charge you are bringing where potential is V2. Due to electric field, I am talking about due to electric field, right? So the potential at this point is V2. Now if you are bringing charge Q2, so the work done will be equal to what? Q2 into V2 you can easily write. But the thing is that we are only considering electric field. We are not considering the external charge. But here external charge is available. So we have to also use this concept. What concept? See here, if charge is Q1 and there is a charge Q2, if there is a potential V1 and the potential is V2, so I think we are not consider we will not consider first of all mutual. We are considering only the electric field now. Okay, and we are not considering later. I will consider. So this is the electric field, and the potential is at this point is Q1, and potential at this point is V. V2, and potential at this point is V1. Now, the work done for one is equal to Q1 V1. Work done for 2 is equal to Q2 into V2. Now the thing is that when you put this body, extra electric field or external field will be created by this charge. So due to this system of charge, how much work is done? So that is equal to 1 and 2. Work done in corresponding work 2 will be equal to K Q1 Q2 by R12. Just now we have derived this, right? So finally total work done will be equal to, we have to add all the three. So if you will add, so total work done, that is net work done, will be equal to Q1 B1 plus Q2 B2 plus K Q1 Q2 by R12. So finally you will get this. So I hope you have understood this. See here, potential energy of a system of a two charge is equal to, so by definition W1 will be equal to Q1 V1 and W2 will be equal to Q2 V2 plus K Q1 Q2 by R12. When you add this, so you will get total potential energy of the system is equal to Q1 V1 plus Q2 V2 plus K Q1 Q2 by R12. This is the condition when system of charge placed in external electric field. I hope you have understood now. Now we will go for next, that is electrostatic of the conductor. So let us discuss more about the conductor, right? Electrostatics of the conductor. Inside the conductor, electric field is zero. Very important. Let us consider this is a conductor. So electric field at this point is zero. Right. This is very important. At the surface of the charged conductor, electric field must be normal to the surface at every point. Suppose this is the surface, so normal always, no matter what the shape is, always there will be 90-degree, right? So this is the second point you have to remember. Okay. Now the third point is the interior. The interior of a conductor can have no excess charge in a static situation. Inside the conductor no excess charge is there. Next, fourth is your electrostatic potential is constant throughout the volume. See, throughout the volume, if I am considering that at point A potential is A, at point B potential is B, when you move the charge, so no extra work you have to apply, no effort is being applied. It means that work done is equal to 0. So work done from moving a charge from A to B divided by Q is equal to VB minus BA. Now work done from A to B is equal to 0. So from here we can say that potential difference is also 0. So finally, potential at A and B both are equal. So electrostatic potential is a constant throughout the volume of the conductor and has the same value as it is inside or outside. So I hope you have understood now. Now next is for question number, next point is your fifth point. Electric field at the surface of a charged conductor is E, where sigma is surface charge density, which may be positive or negative, and is the unit vector normal to the surface of the surface in the outward direction. Now let us consider this is the same, right? Now I will tell you that you have to do it by your own. Try to do it by your own. So let us consider this is the surface, and I am making a Gaussian surface, right? I am making a Gaussian surface. So if I will make a Gaussian surface, so I want to find electric field at the surface of the charge. So if you want to find electric field at this surface, so what will be the electric field at this surface? So it you can use the Gauss concept. If you will use the Gauss concept, so you will find electric field is equal to at the surface is equal to charge density by sigma, right? Charge density by sigma, as sigma by epsilon r, and the direction will be n cap, that is area vector, right? Now let us discuss about the sixth point. It is that electrostatic shielding. What is electrostatic shielding? It is the phenomena of protecting a certain region of the space from external electric field. Now the thing is that we know that any cell, the charge is only outside, and inside there is electric field is also zero, and charge will also be zero, right? So inside, if there is no charge density, so what will happen? If a conductor contains a cavity like this is the cavity. See, this is the cavity here. And if no charge is present inside it, definitely in this cavity, no charge will be there. Cavity, then there can't be no net charge. A charge anywhere on the surface of the cavity, charge will be, see, at the surface here, you will get the charge at the surface, right? This means that if you are inside the charge conducting box, you can safely touch any point or inside the wall of the cavity without any shock. Yes, because most of the charges are like this. So what will happen if there is a cavity and you are inside this cavity? So what will happen? What will happen? You won't find any shock. So I have given a diagram. So from here you can understand what I mean. See here, this is the cavity, and from outside you are giving a charge. But in charge, so what happened? The top layer of the surface contain only charge, but inside there is a no charge, so there will be no shock at inside the cavity. So this is the fundamental basic concept. Okay, and this phenomena is called electrostatic shielding. Seventh point: if an uncharged conducting plate is placed in a region having an electric field, then due to the electric force on the free electron in a conductor redistributes themselves till the electric field produced due to the redistribution cancel the original external field, and hence the net field inside the conductor is zero. What do you mean by this? See, you know that this is a normal conductor. This is normal conductor. There will be positive, negative charge, positive charge, negative charge, positive charge, negative charge, like this. See, when you apply an electric field in this conductor, so what will happen? When you apply, so what will happen? The force will be applied on positive as well as negative charge. You know that positive will move in the direction of electric field, and negative will move in the direction of opposite to the negative field, opposite to the electric field. So here we can see that most all the charge, negative charge, is against the electric field, right? Against the electric field, and it settled here, and it also settled here. Till which point it settles? See here. For example, if you have applied an electric field, that is equal to 100 Newton per meter. Now what happens? It redistributes the charge. Due to this, what happens? The charge in the conductor redistributes. Now, as soon as it starts redistributing, so what will happen? This is positive and this is negative. So electric field inside will be created, which is just opposite to the outside electric field. So let us consider starting its value. Inside, the value of the electric field is 10 Newton per meter. After a while, it increases to 50 Newton per meter. After a while, it also increased to 80 Newton per meter. So till that time, so charge redistribute themselves like this: negative, 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 positive, positive, positive. Now the time came when electric field become 100. So what will happen now? So outside electric field and inside electric field will cancel out each other, and they will become A net is equal to 0. And after that, no distribution of a charge, no displacement of charge will happen. And this is how the net electric field inside this conductor will become a 0. So I hope you have understood now, right? Now the eighth point is a non-uniform charge conductor. A non-uniform charge conductor means the charge conductor is non-uniform in a size. Have a charge density at a different at a different points. So here charge density is different, here charge density is different. So the surface charge density is maximum where the radius of the curvature is minimum. So let us consider the radius of the curvature. See if see here, everywhere you can draw a radius of the curvature. For example, I want to make at this point, I want to make the radius of curvature. So I will make a circle like this. So this will be the radius of curvature. Now at this point, if you want, so you can't draw here because its radius of curvature is small. So it will create a small hole like small like this. Since the radius of curvature is more, so density is less. Radius of curvature is less, density is more. So the density will always inversely proportional to the radius of the curvature. It means that the radius of curvature is more means what? Sigma 2 is less. It means that from here we can conclude that the density at 2, that is sigma 2, is less than density at sigma 1, right? And this happens due to the radius of curvature. So I hope you have understood the radius of curvature concept, right? Now, very important topic, that is your dielectric topic. Here, what is dielectric? Dielectric are insulating or insulator non-conductive material which transmit electrical effect without conducting. So it won't conduct, right? It won't conduct, but charge will be on the surface. It won't conduct. If you pass an electricity, if you create a potential difference, so what will happen? No movement of electron will happen. Okay. Now there are two type of material, that is polar dielectric and non-polar dielectric. So I will discuss both of them. So what is polar dielectric? So this is very important. If the center of the positive and negative charge do not coincide because of asymmetric shape, the molecules then are called as polar molecule. It is like polarization, right? Polarization means what? Let us consider. Have you heard about the board polarization? If you, if see here, if you and your friend both want to share something, let us consider, or you can also consider here chlorine and hydrogen, right? This is a very good example. So the size of the chlorine is large, but the hydrogen is small. So what will happen? What is happening here? There is one minus charge and there is one plus charge. So what will happen? It will share the electron, or electron sharing will happen, or bond will be there. Bond will be made here. Right, this. So when bond will be made there, so what will happen? There will be no charges because it has transferred, hydrogen has transferred this to the chlorine, right? Now what happens? Since chlorine is or powerful, and they are sharing the electron equally, So the power should be equal, but what happens? Chlorine has a big size. So it tries to pull the hydrogen electron toward this. So when it will pull, what will happen? It means that it want to take. So what will happen? The partial charge will be created at the chlorine, and partial negative charge and partial positive charge will created on the hydrogen. So it means that there is a polarization. It means that it is powerful, so it want to attract its electron. Same thing happens here. See, it is hydrogen and hydrogen, so both are small. But what happens? Oxygen wants to attract at this point. In spite of sharing the electron, they want to attract. Since you are sharing, for example, you and your friend both are sharing some properties, right? Or you have you and your friend both have done a business, and your friend has given $5,000, $5,000, and you have also given a $5,000, and you have both have made a business. But thing is that your friend is powerful and always want your conditions to be there in his side. If he want to make some meeting and all, so what will happen? It will try to tell you that you come in toward me, because he is powerful, and you will hear him. The person who is powerful, you will try to be attracted on that side. So here also oxygen is powerful. So what happened here? Charge is being attracted toward the oxygen. So what will happen? Partial negative charge is there created. Partial negative charge will positive charge will be created. Now since equal and opposite charge is created, so what will happen? Dipole moment, and dipole moment is from negative to positive, so dipole moment will be created, right? So this is known as polar direct dielectrics, because here polarization happens, right? Now what about non-polar dielectric? The molecule in which the center of positive charge coincide with the negative charge and are called the polar molecules. Why center are coinciding? Why? Because they are not getting shifted. All are equally powerful. For example, hydrogen and hydrogen both are equally powerful. So what will happen? They are not trying to shift each and every one. Here carbon, oxygen and CO2 are powerful. All are powerful. So what will happen? There will be no polarization formation. So such a molecules are symmetric in shape, and we can call say as collective dipole moment is also zero. So for non-polar dipole moment, net dipole moment is equal to zero. For a polar dielectric, net dipole moment, that is P is equal to not zero, right? So these are the basic two difference. Now dielectric polarization, when a non-polar when a non-polar dielectric is held in an external field E, the center of positive charge proton in each molecule is pulled in the direction of E, and the center of negative charge electron is pulled in the direction of opposite to E. This is known as dielectric of the polarization. I will explain you. Okay, don't worry. See here. I will discuss about these molecules. So where dipole moment is zero. See here, this is your non-polar dielectric. So the net moment is zero. So here what will happen? Net moment is zero. So see here, this is your non-polar molecule. So electric field. This is your external electric field. This is your external electric field. Electric field. So this is an external electric field. So this is zero. So when zero, what will happen? Since it is a polar molecule, so no dipole moment is there. So what will happen? Dipole moment is zero here. Dipole moment is zero, because every atom has a dipole moment zero, right? Or every molecules has a dipole moment zero. So overall dipole moment will be zero. Now the thing is that when you apply an external electric field is not equal to zero. There is an electric field like this. So what will happen? See, positive will go with the direction of electric field, and negative will go with inside opposite to the electric field direction. See here, negative charge is going toward this. Earlier, what happened? Both are at the same place. See, But after this, what happened? Negative charge go like this, positive charge go like this. So same thing happens with each and every molecules. So when this happen, it means that the smaller E1 is created, E2 is created, E3 is created, right? And each small electric field, En is being created. So each small electric field will create a huge electric field inside the inside the huge electric field inside the non-polar molecules. So what exactly happens? See here, you try to give the direction. See, inside there is a direction of the electric field will be from positive to negative. So this will be there, this will be there, this will be there. In this direction, there will be a electric field. In this direction, positive to negative. So what will happen? Net electric field will be not equal to zero, and dipole moment will be created, right? So dipole electric field is in this direction, but dipole moment is in this direction. So net dipole moment is not equal to zero when a non-polar molecules is placed at the inside the electric field. Therefore, the two center of positive and negative charge in the molecules are separated, and the molecules get distorted, and it is said to be polarized. Here, net dipole moment happens, so that's why this is known as polarized. And how this has been polarized? There was no polarized molecule earlier when there is no electric field, but after applying electric field, we can say that there is a polarization, right? So I hope you have understood the polarization phenomena. Now let us go for a polar molecules. See, I have already discussed about non-polar molecules. Now what about non polar molecules? See, for a polar molecules, when no external field is applied to a dielectric with the polar molecules, then the different permanent dipole are oriented randomly due to the thermal agitation, and so the total dipole moment is zero. See what happens? See, this is polar molecules. So polar molecules, what happens? If we have already discussed that what happens to the polar molecules, there will be a dipole moment, right? Everywhere there will be a dipole moment. You can't say that dipole moment is zero for polar molecules. See here, the dipole moment is in this direction. Dipole moment is in this direction. See, the direction of dipole moment is from negative to positive, right? So this will be like this, negative to positive. So direction of dipole moment will be negative to positive, negative to positive. So overall, when a molecule is seen, polar molecule is seen, see, due to its orientation and agitation, suppose the dipole moment in this direction is P1, so and another dipole moment is also P1, same magnitude, so net dipole moment will be zero. Same thing happens here. The each and every molecules are oriented in such a way that net dipole moment will be zero if there is no electric field. External electric field is zero here. So polar molecules as well as non-polar molecules both have a dipole moment zero, or net dipole moment is zero when there is no external electric field, right? Now, when an external electric field is being applied, so what will happen to an individual dipole moment tends to align itself when a over all molecules, then there is appears some net dipole moment in the direction external to electric field. So we can say that dielectric is polarized. See, as soon as no electric field is there, so it is randomly placed. See here, it is randomly placed, right? It is randomly placed like this here. So net dipole moment was zero. But when you apply an electric field, so what will happen? Negative will try to go against the electric field, positive will go with the field. So what will happen? It will try to make a sequence like this. So when this happens, so what will happen? Net dipole moment will be created. So net dipole moment is in this case is also not zero. Okay. So now I hope you have understood this. Now let us go for electric susceptibility. Now see, try to concentrate here. It is found that the electric polarization P is directly proportional to the effective electric field in a polarized electric field? What do you mean by effective electric field? P is directly proportional to the effective electric field. What do you mean by effective electric field? See, very important. This is our E naught, and this is electric field is of the polarized molecule, right? So the polarization is directly proportional to the external electric field, right? Polarization is directly proportional to the external electric field, right? See here, it is found that electric polarization, that is P, is directly proportional to the effective electric field in the polarized electric. What is effective electric field? See here, external electric field is E naught. Internal electric field due to the polarized molecule is EP. So the effective electric field, that is E will be equal to E naught minus EP. Okay. So the effective polarization, polarization, polarization can be, see here, polarization can be told that it is directly proportional to the effective electric field. That is, it is not E naught. So you can write here P is directly proportional to the effective electric field. So P is equal to zeta into E. It is not E. It is again I have done the mistake. It is not E naught. So it is the effective electric field, right? Effective electric field, where chi is called as electric susceptibility of the dielectric. Okay. Now you need to find E. Okay. So polarization is equal to net dipole moment per unit volume is also known as polarization P. And here the electric susceptibility describes the electric behavior of the dielectric. For vacuum, susceptibility is 0. Now effective electric field in a polarized dielectric is E is equal to E naught minus EP. E is, from here we can say that is equal to 1 by K. Why 1 by K? Because E is directly proportional to the E naught. If you increase E naught, so the effective electric field will be also increased, right? See here. Externally, if you are applying E naught, if you are increasing E naught, so what will happen? Effective electric field will increase. So what will happen? Polarization will up. See here, net electric field also will be increased. If you increase the external electric field, so the net electric field will also increase. See here, E is equal to E naught minus P. But after certain limit, EP will be, if we want to increase. So finally, we can say that E is directly proportional to the E naught. And if you increase E, so E naught will also increase. So finally, we can say that here E is equal to E naught by K, where K is your dielectric constant of the material. So it means that if you put between a charge, there is a dielectric medium. So what will happen? It will try to decrease the electric field here. Thus, the effect of a dielectric is to weaken the field inside the dielectric slab. So this is very important. So this is the very important that the net, why we put the dielectric on the parallel plate, or the uh, field inside dielectric slabs are there. So if you put any dielectric medium, so what will happen? It will weaken the electric field. So I hope you have understood this basic concept. So by using this basic concept, we will discuss the capacitor, parallel plate capacitor, and lots of things are there to learn. So this is part 3 video. I will complete end up this session here only for your if you want a continuous videos, so be updated and subscribe our channel, because I'm updating the chapters series by series, and I will come for next fourth class, that is part 4, and I will discuss there about capacitor. So thank you. That's all for today. Thank you for watching our video. Thank you.